Graphing qualitative variables. When the Apple computer introduced the iMac computer in August 1988, the company wanted to learn whether the iMac was expanding Apple's market share. Was the iMac just attracting previous Macintosh owners? Or was it purchased by newcomers to the computer market and by previous Windows users who were switching over? To find out, 500 iMac customers were interviewed. Each customer was categorized as a previous Macintosh owner, a previous Windows owner, or a new computer purchaser. This section examines graphical methods for displaying the results of the interviews. We'll learn some general lessons about how to graph data that fall into a small number of categories. The key point about the qualitative data that occupy us in the present section is that they do not come in with a pre-established ordering, the way numbers are ordered. For example, there is no natural sense in which the category of previous Windows users comes before or after the category of previous iMac users. The pie chart in the figure shows the results of the iMac study. In a pie chart, each category is represented by a slice of a pie. The area of the slice is proportional to the percentage of responses in the category. Although most iMac purchasers were Macintosh owners, Apple was encouraged by 12% of purchasers who were former Windows users and by 17% of the purchasers who were buying a computer for the first time. Pie charts are effective for displaying the relative frequencies of a small number of categories. They are not recommended, however, when you have a large number of categories. Pie charts can also be confusing when they are used to compare outcomes of two different surveys or experiments. In an influential book on the use of graphs, Edward Tufts asserted the only worse design than a pie chart is several of them. Here is another important point about pie charts. If a pie chart is based on a small number of observations, it can be misleading to label the pie slices with percentages. For example, if just 5 people had been interviewed by Apple computers and 3 were former Windows users, it would be misleading to display a pie chart with the Windows slice showing 60%. With so few people interviewed, such a large percentage of Windows users might easily have occurred since chance can cause large errors of small samples. In this case, it is better to alert the user of the pie chart to the actual numbers involved. The slices should therefore be labeled with the actual frequencies observed, example 3, instead of with percentages. Bar charts can also be used to represent frequencies of different categories. A bar chart of the iMac purchases is shown here. Frequencies are shown on the y-axis and the type of computer previously owned is shown on the x-axis. Typically, the y-axis shows the number of observations rather than the percentage of observations in each category as a typical in pie chart. Often we wish to compare the results of different surveys or of different conditions within the same overall survey. In this case, we are comparing the distributions of responses between the surveys or conditions. Bar charts are often excellent for illustrating differences between two distributions. This figure shows the number of people playing card games at the Yahoo website on a Sunday and on a Wednesday. We see that there were more players overall on Wednesday than on Sunday. The number of people playing Pinochle was nonetheless the same on these 2 days. In contrast, there were about twice as many people playing Hearts on Wednesday as on Sunday. Facts like these emerge clearly from a well-designed bar chart. Don't get fancy. People sometimes add features to graphs that don't help to convey their information. For example, three-dimensional bar charts like the one shown in the figure are usually not as effective as their two-dimensional counterparts. Here is another way that fanciness can lead to trouble. Instead of plain bars, it is attempting to substitute meaningful images. For example, this figure presents the IMAC data using pictures of computers. The heights of the pictures accurately represent the number of buyers, yet the figure is misleading because the viewer's attention will be captured by areas. This can exaggerate the size differences between the groups. In terms of percentages, the ratio of previous Macintosh owners to previous Windows owners is about 6 to 1. But the ratio to the two areas in this figure is about 35 to 1. A biased person wishing to hide the fact that many Windows owners purchased iMacs would be tempted to use this figure rather than the simple bar chart. Edward Tuft coined the term lie factor to refer to the ratio of the size of the effect shown in the graph to the size of the effect shown in the data. He suggests that lie factors greater than 1.05 or less than 0.95 produce unacceptable distortions. Another distortion in bar charts results from settling the baseline to a value other than 0. The baseline is the bottom of the y-axis, representing the least number of cases that could have occurred in a category. Normally, this number should be 0. This figure shows the IMAC data with a baseline of 50. Once again, the difference in areas suggests a different story than the true differences in percentages. The number of Windows switchers seemed to minuscule compared to its true value of 12%. Finally, note that it is a serious mistake to use a line graph when a y-axis contains merely qualitative variables. A line graph is essentially a bar graph with the tops of the bars represented by points joined by lines, the rest of the bars suppressed. This figure inappropriately shows a line graph of the card game data from Yahoo. The throwback to this figure is that it gives the false impression that the games are naturally ordered in a numerical way. To summarize, pie charts and bar charts can both be effective methods for displaying qualitative data. Bar charts are better when there are more than just a few categories. Avoid creating misleading graphs.